Hi guys. So I checked your syllabus and I did see that you guys only focus on the acid dissociation constant. Also for the base dissociation constant, you're just not the base but rather the basic how basic stuff works. They only expect you to explain them, not calculate them. Okay, so there's a question here. Oh, this is not a buffer, but it's just an acid. So this question is about acid. In chlorethanic acid is a weak monobasic acid. Write down the Ka expression for chlorethanic acid. So remember, this acid will dissociate to give us CH2COO minus. Don't forget to include the square brackets because they mean concentration of. Then over ClCH2 COOH. So that's the concentration of the acid. Okay. So concentration of the product over the concentration, sum of the concentration of the product over the concentration of the acid. So how this expression can be simplified. This expression here in 1 can be simplified to the expression in 2. How? Remember, we spoke about this. The concentration of this ion can be equated to the concentration of the H plus ion. Yeah. So the concentration of the base, the conjugate base, can be equated to the concentration of the H plus. So a student carries out an experiment to determine the pKa value of a solution of Cl, the chlorethanic acid. The concentration is given, the pH is given, and then use the expression in 19.1, which is this expression here, to calculate for the value of pKa for this chlorethanic acid. So remember, here on this expression, we don't have the concentration of the H plus. So that's what we need to do. We are given, however, that the pH of chlorethanic acid is 1.95. So remember that pH means negative log of H plus. And I've always been saying that P means negative log of P. So pH is 1.95 is equal to negative log of the concentration of H plus. Therefore, the concentration of the H plus ions is equal to 10 to the power of minus 1.95. So this is always to base 10. This is something that people don't speak, but it's base 10. So it's a log in base 10. So now the concentration of the H plus ion would be given 0.01122 moles per dm cubed. So, okay, now we have the concentration of the H plus. We have the concentration of our acid. It's given here, 0.09. We can then find Ka. So Ka is equal to 0.01122 squared over 0.09. Then we can find Ka. Then pKa, again, is the negative log of Ka. So P is negative log of. So then what is Ka there? 0.01122 squared over 0.09, getting 0. Okay, let me not write like that. However, I can say it's 1.399 times 10 to the negative 1, 2, 3 times 10 to the negative 3. So pKa is negative log of that, which is 2.85. So that's pKa. Okay, done with that part. We can move on. A student titrates 10 cubic centimeters of a sample of ethanoic acid against what? An aqueous solution of that concentration of barium hydroxide. Then now, ethanoic acid plus barium hydroxide, the reaction is given to give barium ethanate and water. The student used the pH meter to measure the pH of every addition of barium hydroxide throughout the titration, and the results are shown below. So the results are here, and you can see following an S curve is expected. Now the question says draw a best fit curve on the graph and calculate the concentration of ethanoic acid solution. So the best fit here is you just have to connect these points, but you don't connect them in a straight line. They are connected in a smooth curve. Okay. In a way, you don't need to have this, it ruins your graph. So must be straight, like this, like this, like this. Connecting all the points, connecting all as many points as you can. Maybe not all, but as many points. Yes. And remember, somewhere around this point, somewhere around here, that's where we have the equivalence point, the equivalence point. Well, the equivalent point is known in maths as the point of inflection. This is the point with the highest gradient. This is where the number of moles of barium hydroxide added are equal to the number of moles of the acid. So, okay, the number of moles of the acid are equal to the number of moles of barium hydroxide. So, the question is asking us to calculate the concentration of ethanoic acid. Well, to calculate the concentration of ethanoic acid, we need two things. Concentration is number of moles over volume. The volume is given. The students titrates 10 cubic centimeters, a 10 cubic centimeter sample of ethanoic acid, but we don't have the number of moles. However, we can get the number of moles of ethanoic acid from the number of moles of barium, of barium hydroxide. So if we can calculate the number of moles of barium hydroxide, we can then get the number of moles of ethanoic acid. There are two times. So here we're given that the concentration is 0.056, and we know that at this point, at our equivalence point, uh, here, this is where the number of moles of barium hydroxide are equal to the number of moles of what ethanoic acid required. So looking at this, okay, my line is a bit skewed, but looking at this, I can see that the point is around 12.5 cubic centimeters. 12.5 cubic centimeters of barium hydroxide is required for the neutralization. So we now have number of moles of barium hydroxide is equals to 0.056 times 12.5 over 1,000. Then we can get the number of moles of barium hydroxide. But now the number of moles of sodium of ethanoic acid is 2 times the number of moles of barium hydroxide, which is 0.056 times 12.5 over 1,000 times 2. I'm getting 0.000014 moles. Then now to get the concentration of ethanoic acid is just this number of moles over 0.01. Concentration is 0.0014 over 0.01. which is 0.144. Okay, done. Now, the endpoint of the titration can be found by observing the color of an indicator. The pH ranges are shown of the indicators. Identify the indicator in the table that will be the most suitable to observe the endpoint of the titration between these guys. So now the indicator is most suitable is the one which is close to the equivalence point. So the more your indicator like works is the pH range is close to the equivalent point, the better it is. So now we see that here we have a weak acid reacting with a strong base. So then we expect that our equivalence point should be greater than 7. So as you can see here already also that, okay, confirming our endpoint is greater than 7. So we need an indicator which works above 7. So when looking at these two guys, at this table, you can see that two guys here have ranges which go above 7. So phenol red and phenolphthalein can both be used to show the endpoint of this reaction, the last two. Okay, so now I'm going to pause and then I will okay guys, so on this question, this is a buffer question. So okay, it says butanoic acid is a weak monobasic acid. Explain what is meant by the term monobasic acid. So a monobasic acid, 1 mole of acid dissociates to give 1 mole of H plus ion. Okay, so 1 mole of acid dissociates to give 1 mole of H plus ions. Monobasic. Okay, cool. Then the next question says a buffer, a buffer solution. A buffer solution is prepared by dissolving 3.39 grams of potassium hydroxide in 250 cubic centimeters of 0.367, okay, moles of butyric acid. The buffer solution is a pH of 5.05, 5.07. Calculate the Ka of butyric acid. Assume that the volume of the solution remains constant. So the volume of the solution remains constant after the addition of potassium hydroxide. So this stuff which is in blue, I was doing it before I enabled this recording so that I don't take my calculator often. But okay, so remember guys, the HH formula, Hansel or not Heisenberg, but Henderson Hasselbeck formula. pH is equal to pKa plus the log concentration of salt over the concentration of acid. So here we're given that it's a buffer that is being prepared. We're given that there is a butanoic acid which is of this concentration, but actually there's a neutralization reaction first. So because we are adding a base potassium hydroxide, you're adding it to butanoic acid. That's neutralization. A base and an acid is neutralization. So we expect that the neutralization reaction takes place first. And the neutralization reaction, when a base